Hi everyone, I am excited to present Raven, Radar Adaptive Vision Encoders, a CVPR Spotlight paper from Georgia Tech, Green Lab. So Raven is a new deep learning architecture for processing FMCW radar data, which dramatically lowers computation and latency than the existing sensor processing approaches. In short, we achieve state-of-the-art detection and segmentation performance in autonomous driving tasks while using up to 170 times lower compute. So the core problem we are solving here is that the traditional radar pipelines basically collect all the chirps of a radar data for a full frame. Then they apply heavy FFT processing and feed dense 3D tensors into CNN or transformer backbones, fixing latency to at least one frame interval. Lightweight sequential alternatives which have come up struggle in detection performance for two reasons. First, they mix receiver channels too early, discarding the spatial phase information needed for accurate angle estimation. Secondly, what we are trying to solve here is that in DDM radars, as you can see on the figure, that all the transmitters fire simultaneously. So each receiver sees a mixed signal. So if you don't explicitly separate the transmitter contributions, then the virtual array geometry is lost and detection performance degrades. So we basically try to identify which transmitter's information is embedded in which receiver using our new architecture model. So we try to address both the problems with two innovations. First, we introduce physics-inspired spatial mixing. We keep our per receiver processing separate and use a cross antenna attention module to learn virtual MIMO features without ever building any FFT cubes. Secondly, we also introduce a sub-frame early exit inference where we monitor how much new information each chirp adds to the frame and stop processing as soon as the model's internal state stabilizes. Together, these architectural contributions yield up to 170x lower compute and 4x lower latency than the conventional frame-based backbones used in the literature. Now, the key architectural innovation is our antenna attention mixer. So we also introduce so we see that how each receiver channel is independently processed by a fast-time Mamba SSM to produce a compact per-chirp token, which preserves the per antenna phase and amplitude cues. Then we introduce this learnable transmitter query embeddings, which is attended over the receiver tokens via cross attention, acting as a learnable beamformer. The attention extracts the transmitter specific responses hidden in the DDM mixture and pairing, recovering the TX tokens and RX tokens, and reconstructing the virtual antenna features, all without using any range angle Doppler tensor data. So here we look at the complete Raven pipeline. Raw ADC samples flow through per fast SSMs to the antenna mixer into a chirp-wise slow SSM that updates an online state, then goes through a spatial projection and finally decodes through lightweight CNN decoders, producing detection heat maps with box offsets and drivable area segmentation maps, all in an end-to-end streaming pipeline. For the subframe inference, we track novelty by measuring the minimum cosine distance between each new chirp's latent state and all previous chirp states. When this score drops below a calibrated threshold tau, additional chirps offering diminishing returns, and thus we stop our processing in the decoder. We train using multi-chirp prefix supervision. Decoders are supervised at multiple chirp counts, forcing the model to perform reliable predictions simultaneously from the very first chirps. Qualitatively, you can see the adaptive decision module across 4 scenarios. In structured multi-vehicle scenes, the model looks in accurate detections within the first quarter of chirps. In cluster or noisy scenes, it naturally integrates more chirps before halting. Erratic novelty signals tells us when the data quality is poor as well. This means we only spend compute where scenes are genuinely ambiguous. On quantitative benchmarks, full-frame Raven achieves good performance using only 1.02 gigamax and 20 millisecond latency. This is 170 times less compute than trans radar or other state-of-the-art radar models. To ground the practical impact, at Mach 1 speeds, our 9 millisecond detection latency versus the 50 millisecond baseline shrinks tracking error from 17 meters to just 3.5 meters, from 56 feet to 11 feet. So Raven achieves this with under 1 gigamach per inference and roughly 1 million parameters, making real-time onboard radar perception feasible on embedded platforms. We hope this inspires further exploration of efficient physics-informed radar architectures for autonomous systems. Thank you.